So let's look at section 2.3, page 1. Now we're getting into basic differentiation formulas. Well, we've talked about the definition of a derivative, but this can be really time consuming and it can also be very difficult for problems that have extremely high exponents. So we have what are referred to as the formulas or shortcuts for derivatives had we used the long definition. So the first one is if you're taking the derivative of a constant. So notice the variable is x, but x does not appear in our function. The derivative will be 0, right? If my function doesn't have an x in it, then my slope of my tangent line will be 0 across the board because really I have a horizontal line. Next, we have what's the basic power rule. If you have a variable to an exponent, then that exponent will come out front to now be a coefficient, and we will subtract 1 from the exponent. For example, if I had x to the 4th, I'm going to move the 4 out front and subtract 1 from the 4 exponent to now have a 3 exponent. But the key here is that x is in the base of the function, and we'll talk about that more in a minute. As we continue, and not that you need to know the names of the rules, what if we basically had a constant that is a multiple of a function, meaning we have this coefficient out front? Basically, we'll go ahead and use that same power rule derivative formula where the answer will also be multiplied by the coefficient. For example, if I had a 7 in front of my x to the 4th, we know that the derivative of x to the 4th is 4x cubed, but I will need a 7 times that derivative, and 4 times 7 is 28. Next, we have what's called the sum and difference rule, that if there is a plus or a minus, not multiply or division, but in between what you could consider two separate functions, then you can think of your derivative as adding or subtracting, whichever is the case, the terms individually as if they were their own functions. So if I had the trinomial 6x squared minus 11x plus 1, I would think of the first term as my g function, multiply the 2 with the 6 that was already out front. That's a times. It's kind of hard to see. Let me zoom in. Subtracting 1 from the exponent. And even though we're going to multiply the 2 and the 6 to get a 12, we're also going to drop that 1 exponent to become an invisible 1 exponent. Now my g function, which is the first term, has a g prime derivative. If I subtracted the polynomial, I'm going to subtract in the derivative. When we take the derivative of 11x, turns out x just turns into 1. We'll talk more about that in a moment. But then I had 1 times that lead coefficient to get the derivative. And the same thing, we already talked about the derivative of a constant is 0. So after simplifying, I should be writing a final answer of 12x minus 11. Two other derivatives that we don't actually define here are the derivative of the sine is the cosine, and if your function is the cosine, its derivative is negative the sine. Pretty basic, but I did go ahead and show you the coefficient rule still holds. Also be careful if you're writing your minus sign. A lot of people want to write that their answer is 4 minus the sine of x. But remember, we're multiplying that 4 with, well, an invisible negative 1 to get a negative 4. The piece I wanted to point out was we mentioned that the derivative of x by itself is 1. If you think about it, x by itself is like having an invisible 1 exponent. We can bring that exponent out front. We can subtract 1 from the exponent, but that's going to give us x to the 0. Anything to the 0 power is just 1. And so in this case, as I multiply coefficients, I got 1. Here I had a coefficient of a negative 11 that got multiplied with a 1. But as I mentioned earlier, the key is that the variable is essentially in the base, and it may have an exponent you see or an invisible 1. It may have a constant. But if I don't have this format for a derivative, I need to rewrite the question. And to do that, you may need to use some of your laws of exponents. For example, if the bases are being multiplied, we can add their exponents. If the bases are being divided, we can subtract their exponents. Or if we're taking a variable with an exponent to an exponent, we can multiply those exponents. The last rule usually is read in one direction, where if we have a negative exponent, we bring the base and the exponent to the denominator of an invisible fraction, and then we can change the exponent to be positive. But really, we're going to be using this rule backwards, because even though it may feel like you have a base with an exponent, it's in a denominator, and it cannot be in a denominator. But by moving it up top to the numerator and changing the exponent to a negative, we now fit the definition that we need. And the last one to talk about is if you have radicals. Don't forget, you could just see a square root, or maybe you see a square root of x to the 10th, whatever it may be. But what's going to happen is if you think of the number in the caret or the v, that goes down below in your fractional exponent. Whereas since this was technically x over a to the 1, then you can think of it as being multiplied by a fractional exponent. So I kind of give you a couple different examples over here to how to understand it. But it's going to stay x to the a power, but now it's going to become fractional with a denominator of b.